Hi, in this video I'm going to do the last two examples in the class notes for class number 10. And before I get to doing those examples, I just wanted to show you a technique that we use when solving these kinds of far point and near point problems. And it involves this observation we made in class, in the class notes as well, that for the eye, of course, the image distance, the distance from the eye lens to the retina, is staying the same no matter what we change in terms of accommodation, or where the object is, and so forth. So we're going to use that to our advantage when we do the calculation. So suppose we have a lens, and we're told where its far point is. So we have the retina, and we have some lens, P of the eye, and we're told where the far point location is. So we know what this distance is. And then we're asked to find the contact lens correction. And so schematically, what I would imagine doing there is putting in a second power here, a second lens, and maybe call it P sub C for contact correction. And we want to find out how much correction lens, what's the power of the correction lens I need to correct this patient. And so to answer that question, we might reasonably apply V equals U plus P. And to correct, so let me put up here, to find the contact lens correction, we have to remember where is the object when we're correcting. And so when we correct a lens, or a patient's eye, we want them to be looking at an object at infinity, and so the object location has got a vergence of 0. And then the power that would be involved in doing that, so when we're trying to find the correction case, the power would be the combination of the power of the eye and the power of the correction. So I'm going to write those both here. And that should equal, well, it should equal the image vergence, so the vergence of the light waves leaving the back of the lens of the eye, or it's related to this distance here. And that's the distance that doesn't change in the eye, right? The distance from the lens to the retina. But you notice in this problem, I don't know what it is. I haven't been told what it is. In fact, I didn't get told what the power of the eye is. And so that would seem like that's a non-starter. How can we do anything? So we can in fact do something, because we could also apply V equals U plus P for the far point. Right? So imagine having an object right here at the far point, and then no correction lens, right? Just the unaccommodated eye. If there's an object at the far point, it forms an image on the retina. And so we can apply the vergence equation to that scenario. And in that scenario, the power here is just the power of the eye, no correction in there, and it's the unaccommodated eye. Actually, the notes call this P sub U, same thing. And then the image vergence over here, right, is related to the distance to the retina. And so we did examples like that in the notes where we were given the power that we said, suppose the power of the eye is plus 62 diopters, or something like that. And, given a far point location, we could then solve for what the distance is to the retina and so forth, right? But here what we're going to do, so again, still we have a situation where we can have an unknown power of the eye and an unknown lens to retina distance. We don't know what those are. But what we do know is that this vergence doesn't change, right? This image distance here, V, is the same no matter which situation we're in, whether we're in the far point calculation or whether we're calculating for our correction. And so that means we can set them equal to each other. These two V's have to be equal. And so that means these two expressions, this piece here, has to be equal to this piece here. And so I'm going to go ahead and write that we have the correction power plus the power of the eye has to be equal to the image vergence, but the image vergence itself is equal to the far point vergence plus the power of the eye. And you'll notice something really nice. Wrong one. The power of the eye cancels out because it's on both sides of the equation, and we get left with this very nice relationship, which we also saw in the notes we saw that it was true. We did an example, and numerically this is true. This just shows that algebraically it's true, that the contact lens correction is always going to be equal to the divergence of the far point. And what this demonstrates is this nice, useful technique that we can use, writing down the divergence equation for one situation where the left-hand side is the image divergence related to the distance from the lens to the retina, and that's going to always be the same. So we can write down divergence equations for different scenarios and then set them equal to each other because the image divergence is the same. So for example, we could also do that for the near point. So for this similar situation, so suppose we have the same eye, and I'll go ahead and write it the way the notes does, so that's the power of the unaccommodated eye. And then suppose we have some accommodation which allows us to look at some object at the near point. And we would like to solve for, okay, how much power do you need to have? How much accommodative power do you have to have in order to see an object at some location in front of the eye, right? So we'll call that the near point object distance. And so if we apply our divergence equation, right, v equals u plus p to this scenario, we're going to have u of the near point, and then the power that's involved here is the power of the unaccommodated eye plus the accommodated. And again, we might be in a scenario like we are in this example I'm doing here, where we don't know what the power of the eye is. We don't know what the image distance is between the eye and the retina. But we do, but we do know a far point. So if we're given a far point, right? So suppose we're told in this case, the patient has a far point of 75 centimeters, and they want to look at something that's 20 centimeters away. How much accommodative power do they have? That would be the kind of example you might be given. So again, we've got the far point equation up here, which relates the image divergence. And so again, we can set this equation having to do with the far point case equal to this equation having to do with the near point case, because the image divergences have to be the same. So I can go ahead and do that over here. I'm going to say this is equal to u of the far point plus the power of the eye. Okay, so we have set the divergence equation for the near point condition to the divergence equation for the far point condition, because the image divergence for each of those conditions is the same, because the lens to retina distance is the same. And so we again see this nice situation that the unaccommodated power of the eye just cancels out. We didn't even need to know that. And so then we have this relationship, the near point divergence plus the accommodation power is equal to the far point divergence. And so often what we're interested in is the accommodative power. And so that's just the difference between the far point divergence and the near point divergence. All right, and so that's how we can use this useful idea that the image distance for the eyes is unchanged between different scenarios. And so we can relate near point and far point divergences to the accommodative power. Okay, so let's see how to use those examples there in a problem. So this first example here says, consider a patient whose far point for the eye is 100 centimeters, no lens correction. What contact lens correction does he need? And then what if he has a maximal accommodation of +5 diopters, where's the near point? Okay, so I'm going to draw a little picture. I always like to draw a picture to tell myself what we got here. So we have the eye and the retina, and they have some far point out here, which is located. So u far point is 100 centimeters, technically minus 100. And so the first question was, what contact lens correction do we need to stick in here, right? And we can just use that result that the correction should be the far point object divergence. And so in this case, that's 1 over minus 1 meter, so minus 1 diopter. So that would be our correction power, minus 1d. Right, and it just comes from the relationship that the contact lens correction is the same as the far point object divergence. And then it says, we're going to find the near point when he's maximally accommodated. So we could just use our result, but I'm going to go ahead and just go through the calculation one more time because it's useful. So we've got our unaccommodated eye, we have our retina, we're going to stick in some accommodation power, PA, which is going to allow the patient to see somewhere closer, and that's what we're trying to find, right, is the near point object distance. All right, so let's apply V equals U plus P to this. And so in this case, we mean the near point object vergence. And the power is the unaccommodated power plus the accommodation power. And again, we don't actually in this problem know what the unaccommodated power of the eye is, and we don't know where the retina is. But we do know that this all has to be equal to the case up here. All right, so if we didn't really do it this way, but if we had written down V equals U plus P, this would be U of the far point plus P of the unaccommodated eye. And so we can just write that down here, right? Because again, this vergence and this image vergence, these are the same values, right? Because it's the same eye. So we can write that in there, and again, the power of the eye drops out, and we get that the near point vergence plus the accommodated power is the far point vergence. And in this case, the problem is asking us where would an object need to be placed, given that the accommodated power is this amount. So we need to find the object distance. We're trying to find this thing. So let's solve for it. Near point is the far point minus the accommodated power. So the far point vergence we calculated up above was minus 1 diopter, and then they told us that the patient has 5 diopters of accommodation. So this is minus 6 diopters for the near point vergence. And if we calculate the distance that goes along with that, so the little u near point is just 1 over the vergence near point. So 1 over minus 6, which is 16.7 centimeters. Oh, negative. What is the negative telling me? Go back up here. All right, the negative is telling us that it's an object distance up here, right? That it's measured from the lens to wherever the near point is in the opposite direction that the light is traveling through the system. You can just do some checks, right? We got a negative number. Okay, we just figured that means, right, that our near point is somewhere upstream from the lens, and so for a myope that makes sense. The vergence for the near point is larger in magnitude, more negative than the vergence for the far point. That's the same as saying that the position is smaller, and that makes sense too, right? The near point should be closer to the eye than the far point was. So this minus 16 centimeters is compared to the minus 100 centimeters. Good, so that all makes sense. And then let's look at this second example here. Consider a patient whose far point for their eye is 75 centimeters from the eye and wishes to see an object 20 centimeters in front of their eye. Okay. So here's our picture. We have the power of the eye, accommodated power. We have this object 20 centimeters upstream from the eye. We're going to use the vergence equation. This vergence is the object vergence related to this distance. And the power is going to be the power of the unaccommodated eye plus the power of accommodation. And again, we don't know what this image vergence is, but we can relate it to the far point vergence plus the power of the eye. And so our power of the eye is going to cancel out. And in this problem, it's asking us to find the accommodation. How much accommodative demand do they need to have in order to see this thing? So we're trying to solve for PA. So I'm just going to solve for that here. PA equals U far point minus the object vergence of the location we're trying to look at. Okay, so the far point, what was that far point? Let's go up here, just sketch it in here. The far point distance was 75 centimeters. Well, I guess I can put that here. Minus 0.75. And then the object is being placed at 20 centimeters, so minus 0.2. Minus 1.33 diopters. And, oh, I got to be careful here. This is minus a minus, right? The object distance is itself minus 20 centimeters upstream, which is 5 diopters. So this is minus 5 diopters. So this is plus 3.7 diopters. So that's how much accommodative demand you would need to have to see this object 20 centimeters in front of the patient's eye. And just a couple checks. It's a positive value, which makes sense. Our accommodative powers can only be positive. So that was a good thing that worked out. So that was keeping straight these signs over here. All right, so I hope that helps you understand how to do those examples, trying to find near point divergences.